The next topic is DC transfer characteristics. Okay. DC transfer characteristics. Now, whenever we are talking about a DC transfer characteristics, we need to consider both PMOS and NMOS. Okay, so in order to understand the DC transfer characteristics of both together, we will consider a inverter circuit. Okay, consider a CMOS inverter circuit. So if you remember, the basic inverter circuit uses two different types of MOS devices, correct? So the power supply is connected to the PMOS device. So we know that PMOS devices, the sign for a PMOS device is like this. Okay, and at say the end of this, we take the output. Let's denote this as V out, and the input is provided to this circuit like this. This is a NMOS, and input goes to the PMOS as well as the NMOS in this fashion. So this is the V in. All right. So this is a PMOS device. This will be the NMOS device. Right. Now we'll mark some currents here just for our reference. There is a I, that is a current drain to source of a PMOS. Right. Very similarly, this is the I, the drain to source of a NMOS. IDSP for PMOS, IDSN for NMOS. Okay. Now, so when we say we want to look at the DC transfer characteristics, what exactly you are looking for? You are going to look for, you are trying to relate the output voltage to the input voltage, right? So the DC transfer characteristics relate the output voltage to the input voltage of any device, right? But right now we are sticking it to the PMOS and NMOS, right? But this DC transfer characteristic, the word is common for any device. Okay, right? But under it's a you try to relate the output versus input. You plot a graph, right? Assuming there is an assumption. Assuming the input voltage changes slowly, right? This means you cannot expect very fast varying input signal. Input signal should vary very slowly, right? This is the assumption. Only under this condition, the plot you get is considered as the DC transfer characteristics. So we understood which circuit you are using and what you are trying to plot. I give input into the above circuit, which is very slowly going to vary, and I'm trying to plot the output V out, right, as a function of V. This is my ultimate goal, and whatever curve I get is what is called as DC transfer characteristics. Okay, now let we denote few more notations now. So VTN, right, is the threshold voltage of the N channel MOSFET. Okay, similarly I have VTP, we have another term. This is the threshold voltage of which one? It, as the name suggests, it is a PMOS. Okay, Now, so just remember this VTP will be a negative value, right? As we know now, because P channel, right? I want to induce a P channel in the reverse order, right? Okay. Now, what are the regions and what are the values of voltages that needs to be applied for each of the device? We just have to understand first. Okay. So let's write, say, for NMOS. We already know, right? But let's try to write, right? What is a cutoff, right? So I can say if, right, you see the V gate to source voltage of N device is less than VTN, right? VT is a threshold, GS is gate to source voltage. If at all the gate to source voltage applied to the device terminals is less than the threshold, means what? Inactive, it means it is cut off, right? I can actually, that's right answer. So, or I can also denote VGS gate to source of a N device. You can check the circuit, right? So this is the gate, this is the source. So VGSN is nothing but the required voltage only, correct? So this is the drain. So on the other side, you can see this is the drain, this is the gate, and this is the source. So this is how the connections are made for a PMOS and NMOS. All right, let's come down and let's write it. So otherwise, I can either say VGS or I can actually say it is V in itself, correct? So if V in is less than VTN, this means the whole NMOS is in the cut off region. Perfect. Now let's go further. For the same NMOS device, I'm trying to relate the linear region. Okay, so that is if, see, the VGSN is greater than VTN is one condition. I can actually write this as, or this means V in input voltage greater than the VTN. This is one condition, and also I have another condition for the linear region. If you remember, that is V drain to source of a N MOSFET should be less than V gate to source of a N MOSFET minus V threshold. Correct? So otherwise, see what is VDS. Let's go back and check what is the VDS of this. See, VDS is actually measured between these two terminals, correct? VDS means it is V out itself, correct? Hope you are fine with that, right? Okay, so therefore I can write this, the same condition I can write in another way, or VDS is nothing but this is V out, correct? Or V out is lesser than, this is V in minus, because VGS is V in minus VTN. I can write in any of these ways, correct? So if this is the condition, then this means the particular NMOS is in which region? It is in the linear. All right, right. These are the voltages that we use regularly to identify the regions of operation of a MOSFET for NMOS only. Later on, I'll write the PMOS as well, right? So just remember all the conditions so that everything becomes easy for you. You will remember them forever. Okay, right. Then let's go to the third condition, that is if the VGS gate to source of a N MOSFET is much greater than VTN. This is my condition. Otherwise, I can also write this as V in is very big compared to the VTN. This is my first condition. But anyway, we are more familiar with the second condition that we are going to write. That is the VDS of a N MOSFET is actually greater than VGS gate to source of N MOSFET minus VTN, correct? It's bigger, or otherwise you can say that output voltage is bigger than V in minus VTN. If this condition is satisfied, I know that the N MOSFET enters into the saturation. Right. So why these points are important? Because now when we plot the graph, right, we will try to check out which voltage is exceeding what voltage and which is the MOSFET in a saturation, which is in linear and which is cut off, right? We'll try to trace this out. Okay, that's why these voltages are important. Now, what we have written here is for the NMOS, correct? Right. Then, now we'll go for PMOS. So, for a PMOS device that is shown in the circuit, now this is the condition, right? You see, whichever is lesser than for NMOS becomes greater than for PMOS. It's a reverse in polarity, right? So the condition becomes now the V gate to source of a P MOSFET. Look at the previous case, it was less than, now it is greater than VTP, threshold of P MOSFET. That means, right, my other condition could be in terms of, this is the cutoff region, condition for cutoff of a PMOS. All right. So this should be greater than the VTP plus VDD because there is a supply voltage at the top. Okay. Either of these conditions are met, right? Means the PMOS device is in cutoff. Right? High voltage is given to the input, it is off. Lower voltage is given to the PMOS, it is on. Correct? So now see the high voltage is given. Vin is bigger than even the supply voltage, VDD. This means it is off. Okay. Now let's go to the second condition. That is, I want to check out under what condition the device enters into the linear. All right. So this is the gate to source voltage of a P MOSFET is now not greater, it is less than, okay, VTP. Either this is the condition or you can also write in terms of Vin. Vin is less than VTP plus VDD. Okay, this is one condition, right? We can write, okay, I'll slightly write, I'll move it away so that this becomes easy for us to understand. Okay, so let me write here, this is a condition, or I'll write the second condition here. This is Vin less than the threshold of a P MOSFET plus VDD. Okay, this is the condition for this. Otherwise, we are familiar with another version, right? That is in terms of drain to source voltage, that is VDS of a P MOSFET. For N MOSFET, here I write a lesser than sign. I have to write a reverse now. It's greater than the VGS of a P MOSFET minus V threshold, VTP, right? Or you can write the same thing. VDSP is nothing but this is V out. V out. Usually you write a lesser than here. Now you have to reverse the sign because it is PMOS. So this is VGSP is V in minus VTP. So if we find this condition, these conditions met for a PMOS, then you can say that it's in the linear region of operation. All right. And then we go for the third condition, that is if, right, the VGS of a P MOSFET is much lesser than VTP, right? You see, it's a very small voltage, so device has to be turned on completely, right? Or you can write the V in input voltage is less than V threshold plus VDD. It's very less, much lesser than. So I write 2 less than marks. Right, this is one condition. Or you can write in terms of the drain to source voltage, that is VDSP, right, is bigger than, right, VGSP minus VTP. Or I can write the same thing in terms of V out. So V out is less than, much less than V in, right, minus VTP. Okay, so these are the conditions using which you can decide whether the PMOS has entered into the saturation. Okay, so we need these equations later, right? Okay, now also just remember, since the source of the N MOSFET has been grounded, right, we can make the following assumptions, right? So in the given circuit, right, since the source of the n-type MOS is grounded. This means what? This implies I can write V gate to source of n MOSFET itself is equal to V in, correct? And yeah, V drain to source of a n MOSFET itself is equal to V out. Are you okay? Yeah. Right. Also, we will make another assumption so that we can update in the above equations. Whatever set of equations we have written, we can update all these. Right. Also, I can write since the source of the PMOS, since the source of the PMOS is connected supply voltage denoted by VDD. Now you know that this means what is the voltage drop across the gate to source of a P MOSFET. So VGS gate to source of P MOSFET is equal to, this is V in minus VDD. Okay, and I can write the VDS of the P MOSFET. This is related to the output now. So this is V out minus VDD. Okay, right. Now, basically our intention here is to plot the input and output, but again these plot, whatever plot you are going to get is going to vary according to the threshold voltages of both MOSFETs, drain to source currents of both MOSFET, and the beta values of both MOSFETs. Okay, if they are not aligned, in the sense if you don't make them equal for both of them, then you don't get a symmetric curve. Okay, so that point is absolutely necessary to mention here, right? Whenever our target is to score full marks for this question. Okay, so uh, for symmetric DC characteristics, right, we assume the following thing. First thing is that I current drain to source of a n MOSFET is equal to, in terms of magnitude, I ds of a p MOSFET. Okay, I use a sign, I eliminate the sign here because if you consider as it is opposite. DSP goes upwards, DSN comes downwards, so there is a minus sign in between, correct? Yeah. So let's eliminate that again. So V threshold of a P MOSFET should be equal to minus of V threshold of a N MOSFET. It has to be equal. If one has plus 1 volt, other one should have minus 1 volt. This is what is it? Symmetric property. And also we expect the beta value of a N MOSFET is equal to the beta value of a P MOSFET. Under these conditions, yes, it is expected that you will get the proper symmetric curve. Yeah. All right. Yeah. Okay, let's move on. Now, let's directly write the voltage transfer characteristics first. Okay, then we'll try to differentiate the different regions. Under the above conditions, right, the DC transfer characteristics are as follows. Directly, let me write the curve. On one axis we are trying to plot the V in values. Okay, the other will be V out. Okay, now so we have the curve starting from, say, let's write, say this is 0 volts. Let's mark something here. This is 0 volts. If I say this is the VDD, right, same thing, input can also be VDD, output can also be VDD. So I have to write the VDD on this as well. So somewhere at the middle, I'll mark the VDD by 2. It should be somewhere here, the x-axis. Okay, all right. Now, so the curve will start from a point close to VDD. It comes down, okay, and this will reach the VDD like this. This is what is the transfer characteristics. Since it is a inverter, right? Since our circuit is an inverter, the CMOS inverter circuit has been used. Inverter means a NOT gate, right? So you know that. So when the input is low, you see output is high. Okay, and when the input is high, see the output is here. This is the lower voltages. So that's why the circuit is going to work like an inverter, but it's not switching. It's not providing you a sharp uh, transition as expected. Like what I'm expecting is low voltage means this is high voltage. As soon as I get a high voltage, it should be low. This is what we are normally expecting, correct? But since our devices are actually still analog in nature, right? So you see that there is a smooth transition that is happening. Okay, now let's divide this into different regions now. So I'll call, say, this is region number 1. Then I have region number 2, which is surrounding the area of VDD by 2. Okay, so this whole region is what I'm going to call as region 2. Okay, then this region surrounding to VDD by 2, we'll call it as region number 3. Okay, then we have the region number 4 coming up, which is somewhere around this point. Okay, I'll mark the regions with the region number as well. And then at VDD, I have a region number 5 defined. Okay, so let's assume that I'll give a numbers now. So this is region number 1, this is region number 2. Okay, this is the region number 3, fourth region, and fifth region. Now let's mark some of the voltages for our reference. So this voltage is the VT. I'm going to call as on. In order to turn on a N type, I need this much voltage. Okay, so VDD by 2 is already marked. Then this is what I'm going to call as VDD plus VTP. Okay, that's this point. Right. VDD, it should be minus. Sorry, my mistake. Yes. When you write in this way, it's easy. Correct. Every paper you can see one question saying that explain the DC transfer characteristics, right? So wherever we started today, you can start from there. You can keep explain everything, and you can come to this and just explain these curve ones, right? Like region 1, what happens? 2, what happens? 3, 4, 5, and finish. Okay. All right, fine. So this is one part of the curve. Anyway, we are going to explain this in detail now. But in addition to this, I need one more graph to support this. Whatever I'm going to say now, we need another curve, another plot. That is the current. Okay, how much current is going to flow? Right. That is also another very important graph. So let me write this. This is the V in versus the ID, the drain current. You can call IDD, doesn't matter. Okay, drain to drain of both MOSFETs all together. Right. So I will mark the similar regions now. So we already have marked a point here. This is the corresponding VT on. Okay, the above curve, and there is a central point VDD by 2. Let me mark that as well here, and I also have the V in minus VTP and the VDD. So these are the corresponding points. I know that the curve, there will be no current when your voltage is lesser than this, right? So it's not, there will be no voltage, no current. Okay, and current will reach its peak value somewhere here. Okay, and it will, okay, I'll slightly modify, just 1 second. Okay, so let's make it smooth. It will go to a peak value and it will come down. Very similarly, it will come down, 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 and it will reach zero after this, because after this there is none of the device is on, right? So here also device is off. So only in between these regions we have the current flowing on in the in the whole circuit. Okay, so this itself, this plot itself is IDSN equal to magnitude of IDSP. This is the plot what we have, um, the graph which we have plotted here. All right. Okay, so these two graphs are necessary to explain the whole concept. All right, let's move on. Now, we start with the regions one by one. Okay, so this is how it begins. So I'll start the explanation like region number 1. So referring to the first graph, right? What is the condition? In this, you can see that the input voltage provided is less than V threshold of the N MOSFET. We call it as VT on, right? So in this region, what happens? What happens to the N MOSFET? NMOS is in cut off, because, right, I know that the IDSN is equal to 0, no current is flowing, right? And if you check the conditions which we have written earlier for N MOSFET as well as P MOSFET, right, you can check that the P MOSFET is actually in which region? PMOS in linear region. Okay, so because of this implies, you can simply say that the VDSP is equal to the Vout minus VDD, right? As a result, right, you can see that since I know that the VDSP is 0. So since the VDSP is 0, right, but VDSP is 0, drain to source voltage drop of a P MOSFET is 0, right? Because the VGSN is already 0. So this means VDSP is also 0. So put VDSP as 0 here, take the VDD to the other side, what you get? This implies Vout equals to VDD. Are you okay? Make this side 0, take VDD to other side, Vout equal to VDD. Correct? So that means, let's come back to this thing. So whenever this region is the input, output is actually close to VDD. That's what we justified now. All right, with the equations. Now let's move further. So in case of region 2, you just have to check what is the condition. From the graph, the VT on is actually less than the V in is less than VDD by 2. This is the condition we marked on our graph to mark the region number 2. Yeah. Right. So in this case, what happens is PMOS transistor is in the non-saturated region, and NMOS operates in saturation. NMOS enters into the saturation. Okay. Yeah. So PMOS non-saturation and the NMOS enters into the saturation. All right. Now what happens? This implies the Vout output voltage is equal to V in minus VTP. Okay. Yeah. So this is the voltage which you get now if at all the beta n and beta p of NMOS and PMOSs are pretty much equal, right? Yeah. That's what we assumed earlier. Then in that case, we call this voltage as a specific name. It is VOH, right? This itself is denoted by VOH. V in minus VTP is what is considered as VOH. Yeah. Okay, that's the region number 2. Then let's go to the region number 3, right? V in is approximately or very close to VDD by 2. It's surrounding to VDD by 2. If you see that, right, the V in is either very close. You see here, this is very close on the left hand side. This is very close on the right hand side. So the voltage is very close, maybe lesser or maybe greater. Yeah. So in this condition, right, both P and NMOS are in the saturation. Both NMOS and PMOS are in saturation. Yes. So when PMOS will enter into cutoff at a final stage, okay? Because PMOS has to be off, NMOS has to be turning on, right? So under that condition, you will see this, right? So in this case, right, the V out becomes equal to V in. Now just check whether that is already marked. Yes, you can see that, right? This is the V out is approximately equal to V in. VDD by 2, VDD by 2. Input is VDD by 2, output is also VDD by 2. Okay, that's right. So that's why this region is marked as a region number 3. All right, then moving ahead, we have region number 4 as per the graph. What is the condition? Condition is that the VDD by 2 should be lesser than V in, lesser than the VDD minus VTP. Okay, now you see that PMOS is in saturation, NMOS is in the non-saturation. In the sense, NMOS enters into the linear. Okay, so PMOS in saturation, NMOS in non-saturation. Why this is said to be non-saturation? Because depending upon what type of the MOSFET you are using, right? What type of N MOSFET, depletion or enhancement, MOSFET can be either in linear or in cutoff. That's why it is simply said non-saturation, which includes both the other possible regions of operations. Okay, all right. So in this case, the V out is equal to V in minus VT on, and this itself is what is called as VOL. Okay, fine. So that's how the output is measured in this region number 4, which means it is very close to V out L for low. Lower output voltage will come. Just verify. So you see here, in this region, I have a lower voltage coming at the output. Region number 4. Then this is region number 5. So what happens in the region number 5? What is the condition? Let's write first. So input voltage should be greater than or equal to the VDD minus VTP. It means it should be closer to the VDD, right? So what happens? Now you see the PMOS in cutoff, right? And the NMOS in linear, right? So NMOS in linear, PMOS in cutoff. NMOS will pass the right voltage connected to source to the drain, right? So this means what is V out? Now this means the output voltage equal to 0. Input is high, output is low. So therefore, the circuit is working like, right, a inverter. Okay, right. Now, so the next topic is the importance of beta n divided by beta p ratio. So what is the importance of this, right? Now, when we discussed the DC transfer characteristics, we said that they are equal for our assumption, right? But now, so this is the effect of beta n by beta p, that ratio on the transfer characteristics, right? So the effect beta n by beta p ratio on the DC transfer characteristics effect is as shown below. Right, let's write another graph now just to show that what happens if you change the beta ratio. So previously we assumed they are equal, both of them have equal values. But if at all you change, right, you misalign the transistors, right? This is what is going to happen. The V in versus V out was a graph. So now the original case, like somewhere at the midpoint, you are expecting a curve like this, right? So this is the curve where the beta n by beta p is equal to 1. Okay, in a sense, beta n equal to beta p, right? So this curve is meant for the one which we just have plotted, that is beta n equals to beta p. Now what do? You perform the beta n is equal to 10 times beta p. So or beta n by beta p equals to 10. You increase the ratio, right? If you do that, your curve will be like this. Okay, so this is the beta n by beta p equals to 10, or beta p can be moved to the right hand side, making sure that beta n is equal to 10 beta p. At the same time, I have another option, like I can make beta n by beta p less than 1, say 0.1. In that case, your curve will be like this. Okay, so this is the beta n by beta p is equal to 0.1, or beta n is 0.1 times beta p. Okay, now this will give it, we just have to explain this why, right? So this is the answer. So if you want to change the beta n by beta p, right, the channel dimensions will change, right? Because beta is actually directly derived from the channel's dimension, length and the width of the channel. So length by width ratio itself is what is called as beta, right? So now you see, if, or I can write as the beta n by beta p is decreased. If you decrease this, right, what happens? The transition region shifts, right, left to right. You see here, this was here, it is shifted to right. Yeah. Because I decrease this ratio, right? The W by L ratio of a N MOSFET is lesser than the W by L ratio of a P MOSFET. P MOSFET is bigger, bulkier compared to the N MOSFET. That is what is this condition. Okay, at the same time, n MOSFET is bigger, right? I have a circuit n and pmos where n MOSFET is bigger, p MOSFET is smaller. Then this is the result, the red colored graph. Okay, you just have to remember this, that's all. Okay, shifts left to right, and and I can write the output voltage transition is sharp. It's the same thing. The sharpness still same. You see here, here, and here, irrespective of where it actually where the transition happens, it still remains same, right? But normally you see that what we expect is beta ratio of both the transistors should match. Beta n by beta p should remain same. This is what we expect. Okay, then now we have to define few more things before we go to the what is called as the effect of noise. All right, so before that, let's try to define effect of temperature. Yes, you can check the question papers. So we have many questions coming up on this, right? Like there is a main question, and also they'll add a part thing that also explain the effect of temperature. That's for just 2 marks. Main question for some 6 marks, right? So like that. Effect of temperature. Right. Now, why the effect of temperature is important? Because when the temperature varies, mobility of the electrons or the holes will also vary, because they are directly dependent on, right, the temperature, right? So carrier mobility. I'll just write in simple words. You just explain this in your answer. Okay. The mobility, that is mu, right, decreases with increase in temperature, right? So this means, right, the decrease in beta is directly related, so I can write beta is proportional to temperature to the power minus 1.5, or beta is directly related to IDS, drain to source current. So you can write, therefore IDS is proportional to the temperature raised to the power minus 1.5. As the temperature increases, current will decrease. That's the effect of temperature. All right, just explain this itself. 1 mark for sentence, 1 mark for equation. Normally this is a 2 mark question. All right, then we have the next topic, that is input low voltage. Low voltage, if you remember, we already have marked that. That is actually VIL, right? This is how it is denoted, calculated. If you want to calculate the VIL of a given circuit, this is equal to 1 by 8 times 3 into VDD plus 2 times V threshold of a P MOSFET. Okay, then we need another term, that is input high voltage, denoted by VIH. All right, so what is VIH? VIH is calculated as follows. VIH is equal to 1 by 8. Very similar equation like previous one. This is 3 VDD. Now the plus becomes minus. Okay, 2 VTP. Okay, and also there is a relationship between VIH and VIL. Also, VIL plus VIH is always equal to VDD. This is very useful in problems. Okay, moving ahead. Now we define what is called as the noise margin. Okay, we have four types of noise margins defined, right? Directly I'll write the equations. Normally the questions will be coming over there. Okay, so first one is noise margin is denoted by Nm. Okay, and there are four types of noise margins. One is the Nm. This is Nm high. Nmh is equal to, we have two equations associated with them. One is uh, either you can calculate using VOH minus VIH. Okay, this is also equal to the VDD minus VIH. That is noise margin high. Similarly, the noise margin low is defined in the following fashion. This is VIL minus VOL. But normally you can see that VOL is 0 volts, right? In that case, you can make it equal to VIL itself. Okay, whenever VOL is low, VOL is 0, this becomes equal to VIL. Okay, these are the equations that you need to remember to identify that. Okay, okay, so how the noise margins are calculated. Okay, let's try to this. If at all a theory question comes for larger marks, like if it's up to 2 to 3 marks, you can explain just these equations and that's sufficient. But sometimes there is a possibility if it is asked for more than say 6 marks, then what you write is not sufficient, right? Yeah. So then we need to explain further, where let's write what are the voltages, right? The voltage is like VIH is something like, right, VIH, it is minimum high input voltage, is minimum input high voltage. So now VIL is the next term. This is the maximum low input voltage, right? What is the maximum value of voltage you can give as input, which is considered as low voltage? Okay, similarly you have VOL, V sorry, VOH and VOL. So VOL is the maximum low output voltage. Then VOH is the minimum okay. So these are the terms. Now let's try to define the noise margin in terms of the range, the complete range of inputs we have to show here if at all some question is asked. All right, so let me use a graph in this fashion. All right, so here this is output, say this is high and say this is low. So which means anything which enters inside this region is a high voltage. Okay, anything in the lower part is a low voltage. Okay, that means the voltage which is here, this is the least voltage which is denoted as high. So this has to be VOH. Look at the definition we wrote earlier. Okay, similarly, this is this is 0 volts. Okay, and the topmost is VDD. Right, this has to be VOL. Perfect. Right, now on this side I have written the output. At the same time I'll write the inputs on the other side. This is my input side. I'm trying to plot the inputs on this side. Okay, this is input. On the input side, again I need a very similar structure to be plotted. Okay, so I'll use, say, this. On this side, the margin is slightly higher. So say this, I'll say like this. Right, now, so on the input side, this is the low and this is high. Now you see, this voltage is the highest value of the on the input side, correct, which is considered as the lowest value, which is considered as the high value, correct. So this has to be VIH, correct, and this has to be VIL. Right, now you see that if I try to find the difference, see, this much is there is a dilemma here, right? Whether it is high or low, between the input and output, you have a something like a dilemma, right? So this is what is considered as the noise margin. So this is NM, noise margin high, on the higher side. Same thing. This is the noise margin, NM L. Okay, so using this graph, it is very easily you can actually identify, right, what are the noise margins, right? Again, theoretically, it can be proved that there is, you can actually, the typical values can be identified like this. Typical values. So you get a value and you can actually check that whether it is approximately fine. NML, that's a noise margin lower value, is almost 0.46 times VDD. Okay, and the NM high is approximately equal to 0.34 times VDD. These are the approximate values, right? They found after doing after repeating some experiments. Okay, there are the typical values. Fine. Then there are few more terms to be defined. They have been asked for something like a short questions, like 2 mark questions, right? They have added these questions between some other important questions. So those are, the first term is called as a rise time. It's a definition, right? Normally, whenever you give input to a circuit, right? Circuit produces an output depending upon what input value you have provided. Okay, now depending on the input value, for example, a CMOS circuit, when you give an input value high, output should become low, right? Or if you give a input high, output should be from low. If input is given high, means output should be low, or the vice versa. You give a higher voltage, it should tend to become lower voltage on the other side. So you can actually associate the delay of the circuit for providing an output once the input has been given. So I change an input value to from say 1 to 0. It means my output should vary from 0 to 1, right? But it will not happen instantaneously. There is a small delay associated with that. Okay, so that concept is what will be considered as the total delay associated with the circuit. So that delay associated with the circuit, right, is going to be estimated by using two things. One is a rise time and one is a fall time. Altogether you can consider them as the total delay of the circuit. Okay, for which first we need to understand what is the rise time. Okay, all right, so rise time corresponds to, this is nothing but the notation is tau r. Okay, it is, the definition is like this: the time taken by the output voltage V out to reach VDD. From 0 to that, how much time is taken? Okay, so this is the definition: the time taken by the output voltage to reach the VDD. So this can be calculated as this: 3 times CL divided by VDD times beta P. So here VDD and beta values are known, only the CL is not known. This is load capacitance. Okay, then the next term you need to define is called as the fall time. Right, so the it's again denoted by the tau f. Fall time is actually the time required for V out to reach 0. Time required by V out to, I can say, reach 0 volts. So how do you calculate? This is tau f is equal to 3 times CL divided by VDD times beta n. Beta n is the beta value of a n MOSFET. So CL is, once again, it's the load capacitance. Okay, only thing that changes here is nothing but beta n and beta p. So from the above equations, two equations, we can directly write the rise time by the fall time is equal to beta n by beta p. So depending on the beta values of both transistors, right, you can see that you can control the rise and fall times of your MOSFETs. Okay? All right. Fine. Now let's move on for a question. Okay. Find the noise margins if VDD is equal to 5 volts, VOL equal to 0.147 volts, VIL is equal to 0.925 volts, and VIH is equal to 1.8 0.97 volts. Okay, so this is the given data. We have the standard equations already given to us. We need, in order to calculate the noise margin low value, this is VIL minus VOL, right? You can just check the values given here. 0.925 minus 147. So this comes to be 0.778. It's in terms of volts. All right. Then we need Nm high. So this is equal to VIL VIL minus sorry, my mistake. Just verify the correct. VOH minus VIH. Sorry, I'll just correct. So VOH is VDD itself. So this is 5 volts minus this is VIH is 1.97. Correct. So this is 5 minus 1 is 4, 9703, 3.03. Correct. Volts.